Get started. Now, today, as mentioned, we're going to be covering quite a few things in relation to our 1D diffusion equation. This should be enough to really wrap up our discussion of the 1D diffusion equation. This is going to allow us to move into 2 and 3 dimensions, um, both steady state, transient, considering different boundary conditions, considering source terms, and how to solve our system of equations. This is going to allow us then to progress into uh, our convection diffusion problems where we have flow. So for us to round out our discussion of the 1D finite volume method for diffusion, we have to talk about transient behavior, how our system evolves as a function of time. And this will lead into a small discussion a little later in the class about pseudo transients. We're also going to talk about source terms. Source terms are really, really important, especially when we start talking about multiphysics systems. You can have conduction through a material that is also carrying current, and that current might do things such as, cause Joule heating. And how do we model that? And then what we're going to talk about too is our convective boundary conditions for our 1D diffusion equation, considering the implementation of source terms. So I got a little bit to cover today. It's not too bad. Now, let us just refresh our memories. Our general scalar transport equation, put in vector form, can be represented as follows. We have the partial derivative with respect to time of rho phi, where rho is the density of our material of interest and phi is our conserved quantity. So the time rate of change, and when we take the partial, this is telling us how much of our conserved quantity is accumulating within our control volume. Then we have advection, where we have the divergence of our density times our velocity vector times our conserved quantity. And in these situations, we don't have any motion of our medium. So our velocity vector is equal to 0 in advection, and it doesn't exist. Thus, we've been focusing on diffusion, the divergence of our coefficient of diffusivity, gamma, times the gradient of our conserved quantity, and then plus generation. So when we're talking about accumulation and diffusion, we're going to keep these two terms. And by the end of today, we're actually going to have all three terms considered. 75% of our general scalar transport equation will be covered, except this guy encompasses like 95% of the study of CFD. But that's neither here nor there. So let us look first at a transient diffusion problem. Our general scalar transport equation then reduces down to the time rate of change of our density times our conserved quantity phi being equal to that being diffused, i.e. a divergence of gamma grad phi. So we're going to spend a good portion today casting this into our finite volume form. And then I don't have an explicit example of this, or I do, and I just didn't upload it. I'll check over break. And then we can easily look at an example. One of our hallmarks is going to be really comparing this method to analytic solutions, considering our different schemes. So that's going to be the next homework in the pipeline. Now, something we haven't discussed as of yet, and what's kind of cool about CFD is there are 4 rules. And there's 4 rules to the finite volume method. You can think of these as, the rules of artificial intelligence. And these must be obeyed and upheld for the finite volume method to work properly. If we don't adhere to these 4 rules, we can have situations where we're not accurately capturing the phenomena of interest, and we're also having mathematical errors or violations. So let's look at these rules first. The first rule is the flux across an interface between 2 adjacent control volumes, which we denoted previously as J, must be represented by the same expression and must be conserved, unless we dictate by some other conservation equation that it is not. So in a case of conduction, J you could consider as heat, and heat has to be conserved if we have solely a case of conduction. Say we have a rod that is perfectly insulated, The left-hand side is exposed to 200 degrees centigrade, and the right-hand side is exposed to 100 degrees centigrade. We will drive heat through this. We could call that Q. Or in our situation, it's denoted by the variable J. And this has to be conserved. We can't lose heat. Now, if we have a source term, yeah, we can generate heat due to another phenomena. There's a lot of physics that can be modeled by the finite volume method. Our group always specializes on thermometric generators. There's a lot of cool terms that really make this concept a little more difficult. When you talk about a thermometric generator, heat enters one material, and you're actually removing some via the Peltier effect. And part of this heat that's removed is actually producing electrical power. Then as the heat flows through, you have conduction, but you also have a variety of source terms. You have Joule heating, you have Thomson heating, you have Bridgman heating, and all of these are dictated by a different conservation equation. Then also at the bottom, you have Peltier heating. The top is acting as a sink, the bottom's the source. So you have to make sure you capture all those physics. But if we're able to turn off Joule, Thomson, Bridgman, and Peltier, the heat flowing through must be conserved. And that's sensical. So the first rule is pretty easy to uphold. It's really easy to check. So hopefully we don't have too many violations with that. Now, another rule to ensure that our solution makes mathematical sense. Let's look at our stencil, where we have our west cell, our centered cell, and our east cell. Our second rule states that the coefficients of AP and our coefficients of our neighboring cells, i.e. A west and A east, must have the same sign. And we do have that in our equations. Now you say, whoa, you put the others as negative. Well, in the equation we cast, they're all positive. We just kick A east and A west to the other side of the equation to be with AP when we form it. Now, these coefficients have the must have the same sign, and there's a reason for this. For when we are calculating our value in our centered cell, we're looking to the values to the left and to the right. So say our conserved quantity of interest here is temperature. If I have an increase of temperature in my west cell, this has to lead to an increase of temperature in my centered cell. And then as we move down, that's going to lead to a slight increase in the center in the east cell. It would make zero physical sense that if the west cell began to get really, really hot, and we are purely modeling diffusion, that the temperature of our P cell got really, really cold. Is heat flowing from cold to hot to make that happen? I hope not. So when we look at our coefficients, they all have to have the same sign associated with them. This is going to lead to us having a consistent mathematical solution. That's a rule that's pretty easy to adhere to. The third one is when we begin to talk about source terms, and especially nonlinear source terms. And we're not there yet, so just kind of place this one at the back of your mind, and we'll reference it later in the course. But when we have a nonlinear source term, we have to go through the process of linearizing it. And when we do this, the slope of this should be negative or zero, that we'd have a decreasing slope. And this is really hard to explain without us getting into source term linearization right now. So keep it in the back of your mind. This is really just going to require us to have a negative sign associated with the term that's representing the nonlinear contribution of our source term. And this allows us to slowly carry its impact into the solution as opposed to drastically all at once, which then might have our solution overshoot. But we'll put that in the back of our mind. Okay, and last but not least, our fourth rule is related to our second rule. Now, we know the AP has to be sum of our neighboring coefficients. And this makes sense, right? AP is equal to A west plus A east. And when we said they all had the same sign, right, these are all positive quantities. And this has to hold true. Right? Our equation we've cast in our finite volume has to hold true. And what's cool about this is our dependent variable at P. So that dependent variable, pick what you might be interested in modeling. If they increase by some constant value, some just hard offset. If they increase by some offset, this relation has to hold true as well. And a way to think about this is really just universally applying more or less the source term, where every cell is going to be subjected to a constant. And rule 4 really states that when we are modeling source terms, although you might appear rule 2 is violated, it's actually not. So we want to keep these in the back of our mind, and these are going to come up when we start talking about our schemes. And we're going to see this in a little bit. So right now, we will keep rules 1, 2, and 4 at the forefront of our minds, and rule 3 at the back. Now, this is important because when we start talking about our non-steady diffusion equation, there's going to be different ways we can solve this in different mathematical treatments. And if we kind of mess up the mathematical treatment, we can easily violate one of these rules. So we're going to use these to kind of guide us when we talk about our explicit scheme, our Crank-Nicholson scheme, and our fully implicit scheme. Now that we kind of got that out of the way, let us look at our 1D transient transport equation. Now recall we're going to work with this. Del by del t of rho phi is equal to divergence of gamma grad phi. Now, in one dimension, what we're going to do is consider our conserved quantity, once again, to be temperature. We're going to take our diffusion coefficient as kappa, which is our thermal conductivity. And our density and specific heat are going to be assumed constant. So we had del by del t of rho phi was equal to divergence of gamma, oops, that's an F, gamma grad phi. Now, in one dimension, we're going to substitute in T for phi, kappa for gamma, and since we're assuming that our density is constant, we'll just pull this guy on out, but by the product rule, it would jump out anyways, and we'd have the divergence of kappa grad t. So our right-hand side is expressed as the partial with respect to x of kappa, the partial of t with respect to x. Now on the right-hand side, we have to be careful, and we have specific heat added to our system. Can anyone tell me why we have to include specific heat? Can anyone think of why our specific heat should be added to the temporal term? Well, let us look at our units. Del by del x would be 1 per length. Our thermal conductivity is watt per meter K, and then we have K per length. So if we look here on our right-hand side, our temperatures cancel out, and we have watts per cubic meter. Okay, that's on a per volume basis. Awesome. Now, what we'd have here is on our left-hand side, our density is taken as kilograms per cubic meter. Our specific heat is taken as kilojoule per kgk, or we could express this as simply joule per kgk. The kil is not important. And then in our numerator, we have units of temperature. In our denominator, we have units of seconds. So if we go through and cancel out these units, we see mass cancels out, temperature cancels out, a joule per second becomes a watt, so we'd have watts per cubic meter. Now, this really highlights an important point, right? Because we said our change of enthalpy was equal to our specific heat times our change of temperature, right? In this particular instance. And temperature isn't really a quantity that we conserve. There is no conservation law that says temperature has to be conserved. Its energy has to be conserved. So in addition to just us obeying homogeneity on the left and right hand side of our equation, we have to express this in terms of heat. We want to make sure that, we're conserving heat, not temperature within our system. So that's going to be the equation that we're going to cast in our finite volume form. Without C, units wouldn't make much sense, and when you write your code and run it, it would look hideous. Now, what we have here is, let me go back here. We have a PDE, partial differential equation, right? Our temperature, T, is now a function of both space and time. Space in reference to X, time in reference to T. So we have a PDE right now we have to solve. Now, to do this, we have to realize, all right, X, that's a spatial term, and T is a temporal term. So when we solve this, we're going to have to solve it spatially and temporally. So a really easy way to think about this is our x-axis is going to represent our spatial domain. And in our spatial domain, we can apply our stencil to our nodes. So for a given time, say this is our first time step, time t is equal to 1. We can apply our stencil and cast our equations to solve for our conserved quantity at our cell center P. Now, once we go through and we get spatial convergence, we can advance in time. So we're going to move in the y-axis temporally. Now, this is really, really easy to think about. So thus far, hopefully you guys looked at the MATLAB codes. We initialize our temperature field. Then we solve for it. Now, that solution that we get once we have spatial convergence would be used for reinitialization as we advance in time. So you're just taking your previous solution, using that as a seed for your next solution at the following time step. So looking at this, you can kind of think about almost as an old typewriter. We're going to move through our spatial domain, and then we're going to move up a line, and go through a spatial domain again. Move up a line, spatial domain. And really, this scheme is super easy to do. Now, the only difference in this is, in addition to just integrating over our volume, and in the 1D sense, we actually integrated over area, now we have to integrate over time and volume. So we're going to have to do a double integral. But that's not too bad. Okay, now, this is the fun part. Delta X was the width of our cell. I'll call that, I don't know. I mean, it is capital delta. Upside down nobula. Triangle X. Because that is also a delta. So let's call it triangle X is our cell width. And right now we're going to assume we have a uniform grid, but we know how to handle non-uniform grids. And delta X is just the distance in between our cell centers. Now we're going to assume this is all constant. We know how to handle if it's not. So what we need to do is integrate spatially and temporally. So let us look at our governing equation. We had rho c partial t partial x would be equal to partial with respect to x of kappa partial t partial x. We want to integrate over time, and we want to integrate over area of the entirety of this equation. So rho and c are constants. We're going to pull those outside the integral. So we'd have the integral of del t del x, and we're integrating over time and area. On the right-hand side, currently the only constant we'd have would be kappa, and we could essentially pull that out, leave it in there right now. Okay, so when we talk about integrating over area, we want to go between our west face and our east face, because we're trying to determine the change of rho phi in our control volume. So really, when we're going in between these two faces, we're tracing out what's contained in that volume. We're taking this face and we're really sweeping it forward. And this is going to give us our spatial integral, i.e. when we integrated over area previously. Now temporally, we're going to integrate between a time t and a time t plus delta t. So if we just jump back one slide, the difference between our two time steps is delta t. So we're going to set up our integration as such. We're going to integrate between our west and east faces, and that's going to be done in our x direction. We're going to integrate with respect to time between t and t plus delta t. And we're going to apply this to our left-hand side and right-hand side equations. Partial t with respect to t, and the partial with respect to x of kappa partial t with respect to x. So we'll just go through the integration. Let's look first at the left-hand side. We have our density times our specific heat, the integral from our west face to our east face between time of t and t plus delta t of partial t with respect to t dt dx. Now, in this particular situation, we're going to recognize that we need to evaluate our change of temperature between our bounds of t and t plus delta t. And in this particular situation, we are going to be evaluating x, our spatial location, between our west and our east face. Now what we're going to do is x is our spatial position, right? We're moving through our differential volume. So when we evaluate x between our west and east faces, this term boils down to x at our east face minus x at our west face. And then what we're going to have is how our conserved quantity in our celled center t is evolving as a function of time. And we're going to use the subscript to indicate our location within our celled center, and our superscript is going to be our temporal term. So we can call this t of p evaluated at the time step t plus delta t minus t of p evaluated at time t. Now, what we recognize is x evaluated at our west face and x evaluated at our east face, and the difference of these two gives us the value of our cell width, delta x. And what we're going to do is call t plus delta t our second time step, and t our first time step. This is aligned with the picture we drew. Our first time step was when t was equal to 1. Our second time step when we moved a delta t into the future would be 2. So we'll just adopt that convention. So right now we have the temporal evolution of our conserved quantity within our celled center. So that's how we're going to advance it in time. Now, the fun part is the right-hand side. We know how to do the right-hand side, at least when we did our integration with respect to our spatial domain. However, we have our temporal term. So what we're going to do is I have this integral hanging on the outside. And you might have said, well, you had time on the inside and time on the outside in the previous equation. There's a reason for this. We already know how to integrate this equation right here. We've done it before. This is simply equal to our diffusivity at our east interface times the quantity of our conserved quantity in the east cell minus that in our centered cell per the distance between our east and centered cell centers, less the diffusivity at our western interface times the quantity of the conserved quantity at our cell center minus that in our western cell's center per the distance between those two cell centers. So we've already constructed this expression within the parentheses. Now all we have to do is integrate this with respect to time between our two time steps, t and t plus delta t. Now, what we're going to do here is define the following. And this is going to make sense once we talk about our schemes. We're going to introduce a weighting factor. This guy is going to be called f. And f is bounded between 0 and unity. So, for instance, let's just take this one quantity here and let's integrate it. So we could say that this is t of p evaluated at the time step t plus delta t minus t of p evaluated at t, right? And recall, we called t plus delta t our second time step and t our first time step. So we could say that this is simply Tp at our second time step minus Tp at our first time step. And if we're going to integrate it with respect to t, we'd be left with, dt. This guy would convert this to a t, evaluated between the bounds of t and t plus delta t. And doing that, we'd have Tp at our second time step minus Tp at our first time step. This is evaluated at t plus delta t minus that of t. And this is to mean evaluated at, not, multiplied through in a factorial sense. And the difference of this would just be our time step, delta t. So we can see without our weighting factor that we would arrive at the expression that is then underlined red. Now, what we're going to do is apply a weighting factor. And this weighting factor is going to tell us how much of our solution we're going to take from our previous time step and our current time step. Now, if you guys had numerical methods, you're pretty familiar with an implicit scheme. And implicit schemes are really, really nice because you can take somewhat of aggressive time steps and still get a solution. But it's weird to think about that as you're solving your solution, you're using the data from your current time step to populate it. And this works quite well, in a finite difference scheme. If you're using a backward difference, as you move through your domain, you can always pull the most recent values and proceed along. You can do it with the central differencing scheme too, except you have to solve your systems of equations simultaneously through matrix inversion. Doing a brute force for loop's not going to work. So if our weighting factor is unity, we're taking the solution completely from our current time step. There is nothing from our previous time step. If our weighting factor is 0, we are using nothing about our current time step in the calculation of our solution, and we're pulling all the values from our previous time step. So this weighting factor allows us to define whether or not we're going to have an explicit scheme, which pulls all the information from the previous time step, an implicit scheme, which pulls all the information from our current time step, or a mix of both implicit and explicit, i.e. the Crank-Nicholson scheme. So we're going to leave this weighting factor just as is for now. It's incredibly important though. Now we got this cool little weighting factor. What we have to do is work on our right-hand side, right? So the integral between t and t plus delta t with respect to dt of our spatial term, we can break this out rather nicely. This would be equal to our weighting factor times our diffusivity at the east interface per delta xe times te at our second time step minus tp at our second time step minus all that stuff on our west interface and west distance between our p and west cells, and tp2 minus tw2. So this is all really our current or second time step plus 1 minus f, and we have the identical expression. However, now it is at our previous time step. So note that this is not squared. This is in reference to our time step within our system. Now it's somewhat of a messy equation, but it's okay. It's going to boil down very, very nicely very soon. So what we have is in our finite volume formulation, our 1D transient diffusion equation becomes rho c times delta x per delta t of Tp at our second time step minus Tp of our first time step. And this is equal to F, our weighting factor, our diffusivity per our distance between solid centers, T east minus Tp, all evaluated our second time step, minus our diffusivity at our west interface per delta xw, all the same up here. Tp at our second time step minus T west at our second time step. Then we're going to have the quantity 1 minus our weighting factor F, and the identical expression from above one line. Now we're just evaluating at our previous time step. So it is our interest to solve for our temperature in our center cell at our next time step. Because think about it this way. Let's draw out what this equation is telling us. We have our 3 control volumes: west, centered, and east. This is time step 1. I'll call this guy time step 2. And I'll leave a little bit of a space in here. P, east, west. So let's run through a hypothetical. Let's set f is equal to 0. What this is telling us is when we're solving for this quantity, I'm going to be pulling the value from down below here. I'm going to be pulling the value from down to the right and the value from down to the left to populate this one term. And you can see that we are spatially taking the values from our left and right, as well as our previous time step in this calculation. And that would be a fully explicit scheme. Now, if this were fully implicit, say f is equal to 1, what I'm going to do is take the value from my previous time step, TP1, and then my solutions from left and right at my current time step. And right now you might go, well, hold on. As we apply our control volume to our domain, we're kind of moving our stencil from left to right in the x direction. So how on earth are we able to know t east at our second time step when we haven't moved our stencil down here yet to solve for it? And that's okay, because if we solve our equation simultaneously, we can solve for that value while we need it. So that's kind of, what this equation tells us. And it's really powerful right now. So let us do a little algebraic manipulation so we can get TP at our second time step. Now, what we're going to do is call TP at our second time step just TP. And TP at our initial time, we're going to call it TP naught. So this is just, to make life slightly easier. Now, when we do this, right, we have rho c delta x per delta t of TP, which is our definition. And then here I had minus TP1 multiplied by rho c delta x delta t. And we're going to kick that over here. Now we have rho c delta x per delta t of TP1 will just be TP naught, our initial time step. And then we have the remainder of our equations. FKE times quantity TE minus TP per delta XE minus K west per delta X west quantity TP minus T west. We just do that substitution because, oops, everyone calls their initial time step naught. If you want to leave it as 2 and 1, go for it. It's no difference. Now, what we see here is we have a leading coefficient, rho c delta x per delta t. And for you guys that are a little bit savvy, who have done work with CFD or numerics before, you might know what that number or that coefficient is called. Does anyone have an idea?
CFL?
Exactly, Andy. That is your current Friedrich-Louis number, or your CFL number. And we're going to see why this coefficient and the number that it generates, a numeric number, is incredibly important when it comes to the stability of this. Ooh, and during break, I'll find some good videos. I got some really good videos that illustrate this. So we got this leading coefficient of TP2, which we call TP. Now we just got to get all these TP values out. So we broke down that algebra there. What we're going to define is, as we've always defined, our diffusivity per our cell center spacing will be A east and A west. And we'll call AP naught. This will really be your rho c delta x per delta t. We'll define this guy as AP naught. And then AP will be F times A east plus F times A west plus AP naught from your previous time step. Well, actually, that is, oops, I got carried away. This is AP naught down here, because that's evaluated at your previous time step. So you'd have AP naught, A east, A west, A east, A west. So these are going to be our new updated coefficients. Notice A east and A west are remaining unchanged from what we have developed in our code previously. AP is, once again, almost the same. Now we just have our weighting coefficient F leading A east and A west. And then we have to include AP naught from our previous time step. That guy's going to be hanging out. So our AP coefficient updates ever so slightly. And doing that, we can make those following substitutions as listed on slide 13. And once you consolidate, we arrive at our final expression. We have APTP, where we can define AP, just as we did here, is equal to A east FT east plus 1 minus FT east naught from our previous time step, plus A west times the quantity FT west 1 minus FT west naught, plus AP naught minus the quantity 1 minus FA east minus the quantity 1 minus FA west multiplied through by TP naught. Okay. A bit messy, but the hardest part about this formulation thus far has been the algebra. I skipped the steps. We're all good at algebra, right? That's the hardest thing, just getting everything consolidated in our equation. Now, this is good. This is really good. This is our equation now that we can start to cast using our stencil to solve transient problems. But it's all contingent upon our selection of f. Now, let us look at 3 instances of f, and we've kind of alluded to this. If we set f is equal to 0, what's happening is we're going to take everything from our previous time step. So if f is equal to 0, this guy goes away, this guy goes away, and then all we have is this guy goes to unity, this guy goes to unity, that guy goes to unity, that guy goes to unity. So let's look at this. We'd have APTP is equal to A east T east naught plus A west T west naught plus AP naught minus A east minus A west, that quantity times TP naught. In this situation, the temperature terms, i.e. our conserved quantity terms that remain, are all from our previous time step, as well as our coefficient AP naught. And that's calculated on a per time step basis. Okay, so the explicit scheme. The explicit scheme is really, really nice because it's super easy to code up. It's super easy to implement. You can do a for loop and move your stencil down your domain if you really wanted to do that. The way we've solved our equations thus far was simultaneously, but the explicit scheme allows just for a lower level of coding. Now, the opposite end of the spectrum is if we set our weighting factor to unity, we are left with the implicit method, which relies on us calculating everything at the current time step. So if f is equal to unity, that guy goes to 1, this term drops out, this goes to 1, this term drops out, this term drops out, this term drops out. And what we have is we are taking our neighboring values, t east and t west, at our current time step, just as we drew a moment before, and TP naught from our previous time step. So the implicit scheme looked like this in the red, where we took our temperature from our previous time step directly below, and we're taking our neighboring values from our current time step. Implicit schemes are really, really nice. We have to solve them simultaneously, but they allow us to have a high CFL number while preserving stability of our solution. Now, you can pick any number between 0 and 1. And what's incredibly cool is if you generate your own codes for your own research, your own system of interest. If you guys are really just focusing on one set of physics and a really curtailed range of geometry, it's oftentimes easy to build your own code. And what you can do is you can do some tests and see what the best f is. And we're going to talk about what f means in just a moment. And sometimes you see, you want an f of maybe 0.4, 0.6, which decreases computational time, but maintains the same level of accuracy that you're looking for in comparison to a full implicit or explicit scheme. But with that being said, one of the most prevalent values of f is 0.5 or a half. And you blend the two. You have a blend of your explicit and implicit methods. And this is called the Crank-Nicholson scheme. Pretty cool. Someone just said, let's set our weighting factor to a half. And look, now these guys are really famous. And we're going to talk about it. You might see right now hesitant. Why would we blend them? I mean, the implicit looks cool because we're taking the most recent data we generated. Yeah, it requires us to solve system equations simultaneously, but that's just matrix inversion. You go, well, the explicit method's super easy to code and it's just brute force. But sometimes there is a benefit to having both. Now, I think I've been droning on enough. Let's take a little break. It is 5:20. Then we'll get into the explicit scheme. Talk about, oh man, pardon me. Oh, I need some coffee. Talk about the final form it takes. Talk about a few of the limitations of it, especially when we look at a ratio of our time step and cell size. And then we'll go through Crank-Nicholson and implicit. So let us take a, I don't know, 8-minute break. Come back at 5:30. Stretch your legs, get something to drink, use the restroom.
I had a question. Is it possible, I don't know, going through that derivation, it seems like it'd be possible to have temporal refinement so that you didn't need like globally really small time steps if you have spatial refinement in your mesh. Is that possible? Or
So you talking like a localized time step, a non-uniform time step?
yeah.
See, that's interesting because a way around that is really when we're doing that difference, right? It's a backward difference scheme. You're taking the value at time step 2, let's add at 1 per your delta t. One of better instituted methods is in CFX. They actually do a 3-point backward difference. So after your first and then second time step, when you're on your third time step, it's going to take the values from your first and second in the determination of your third. So it's a higher. Don't want to say that correctly. Let me look at my good old numerical methods book. Yes. Aha. So that would be a 3-point kind of backward difference you're doing. And that has error on the order of delta t squared. So as opposed to, doing local delta t for each, say, region where you're applying your stencil, they just do a higher order temporal evaluation, really a 3-point stencil, to make the solution more accurate, which means you could potentially run a higher delta t and obtain the same solution in lesser time with the same resolution, if that makes sense.
Well, yeah, I guess I was thinking like your CFL drives your time step to be really small. But out where there's not quite as small scale of flow, like you don't really need to have such small time steps. So you could just eliminate solving for the whole domain on every time step.
Yeah, I see what you're saying there, because oftentimes there's just one region in your domain that's dictating your CFL, where everywhere else could actually be at a much higher time step, and it'd still have stability. The only thing I'd be worried about then is consistency of your solution, especially in like tracking the evolution of a quantity as a function of time, and being able to get reasonable results out of that. Especially any situation involved flow, having different time scales going on would be horrendous to keep track of.
Yeah.
So yeah, I know what you're saying, because you go, oh man, it's just this one region that's killing the sim, because that mesh is so small. I need such a small DT for my CFL number to be satisfied and have stability. But in these regions, my mesh is so large, I could have such a large delta T. Yeah, I know what you're saying. And that's really the only benefit is moving to a fully implicit method. where you can get away with higher CFL numbers and still keep stability, like CFX does. What CFX is beautiful. You can set whatever CFL number you want, let it rip. As well as if you do pick that higher order temporal scheme. That's really the only way around it currently. Yeah, what really sucks is we say, hey, you want your CFL to be less than a half for stability. But in reality, when you're doing like any high fidelity sim, your CFL is like 0.1. You just go, okay, well, there goes a couple 100,000 hours on the supercomputer. This is great. But that's where some other fancy things like spectral elements, spectral methods comes into play. I don't know, that'd be really interesting to see, at least for consistency of results. If you could have a region that has a lesser time step, I just don't know how passing information spatially that would affect it. Because you'd really want to pass information when everything's at really the same time step or the same physical time. Otherwise, you'd have huge inconsistency of the behavior.
Yeah.
I don't know, something to play around with. Maybe you're onto something, Andy. Maybe you're going to develop this new scheme, but yeah, I don't see why you couldn't like have different time scales within your system, and then once they reach a mutual time, begin to pass them the spatial information. Like if one region had a delta t half of another region, you let that solve that once it hit a mutual place, solve the whole system, and then focus on a small region again, and then pass it back and forth. I think that could be a very useful scheme.
Yeah.
What programming that would be? That'd be horrible. I mean, it'd be doable. It's just, you could lock yourself in a room for a couple months and give it a try. No, you are onto something there.
Because especially just going through the derivation just now, it didn't seem like, I don't know, it would be inherently wrong just on the math side. I could see how like continuity would be tough around where you step down the time scale.
Yeah, because you don't want to pass the wrong information at the wrong time in a transient analysis. But yeah, you could definitely do like localized timescales if you figured out that information passing at the right points. Although I do wonder. I guess I come into another thing we're not thinking about too is like hardware, right? Because you'd have at first huge memory allocation for your domain, do your calculations, go into the refined region where now your array has decreased in size because you're operating on a smaller number of cells. Do those calculations, then bring that information back into the original large array. So you'd almost need some fancy memory system where you could simultaneously have multiple portions of your systems of equations already pre-allocated and cast and operate on, so you didn't necessarily have to reconstruct an array each time and augment its size. Because you've seen with like Fluent or CFX, the pre-computation of just populating the coefficient array is substantial.
Yeah.
Yeah, but I'm sure that's a simple like architecture fix. Something that could easily be done by those smart computer science kids. Yeah. No, you're onto something. Hey, maybe that'll be your project for the class.
I'll make sure to block out a couple 1,000 hours in the coming weeks to figure it all out.
Yeah, let's not do that. You got some other things to do. Oh, okay. Oh, that was a fun hour. So let's jump back in this and talk about our schemes. Now, as I mentioned multiple times already, we have the explicit scheme if we set our weighting factor equal to 0. Now, I've already kind of crossed this stuff out. So anytime you see a term with an f associated with it, it goes to 0. So what we're left with in this particular instance is for our explicit scheme, we'd have APTP is equal to A east T east naught plus A west T west naught plus AP naught minus A east minus A west TP naught. So let us just redraw the picture because visualizing this is so powerful in terms of what this scheme is doing. So when we are trying to solve for our temperature here, TP, we're going to take that, our previous time step in our east cell, that the previous time step in our west cell, our coefficient we calculated AP naught earlier, and the coefficients A east and A west, and then our temperature TP naught. So we're really pulling all the information from our previous time steps. Now notice this A east and A west, these coefficients, they are now being updated based upon our diffusivity and spacing. Now, we're not going to be able to determine those interfacial diffusivities if they say are varying as a function of temperature. We're now assuming that's constant, that gamma is constant, i.e. kappa, and our spacing. So those coefficients, although they are, are reflecting values between the interfaces of our cells. Right now we're assuming they're constant, and that'd just be, what's existing. So really we just, it's going to be the same value at our previous time step. So this is really cool. The explicit scheme, it looks really easy. Just grab the information from your previous time step and move forward. Awesome. Now, we have one of the rules. And the rule that we're going to introduce here is that of positive coefficients. Now, the rule of positive coefficient states that all coefficients, APs, and the neighbors, which is A east, A west, must always be positive. And we talked about this earlier, right? They all have to be the same sign. But what we're going to do here is say they're all going to be positive. So if we have an increase in any of our conserved quantity at any node, we need to see it increase that of our neighbors. Now, this is tremendously important, right? So if we want AP to be positive, we're going to assume A east and A west are going to be positive. Now, what we got here is we have AP naught minus A east plus A west, right? This is the coefficient leading TP naught. How can this right here, how can this be negative? Which would violate our rule of positive coefficients. Well, quite simply, A east plus A west would be greater than AP naught. If that's the case, this coefficient is negative. That's not good. We have a negative contribution from our previous time step. I don't like that. You shouldn't either. Now, what we can do is we know AP naught is equal to rho C, where C is our specific heat, delta X per delta delta X per delta T. A east is our thermal conductivity, or our diffusivity per delta X east, and A west. So what we need is, we said AP naught, hey, just like class all the time. My pen maybe makes it about an hour, and then it just decides it doesn't ever want to write. This is where we were. So we said that AP naught minus A east plus a west less than 0 is bad, right? That's not good. So we want this quantity to be greater than 0. Now, for this, we need A P naught to be greater than the sum of A east and A west. Okay, so let's just write this in. We need rho C delta X per delta T has to be greater than K per delta X east plus K per delta X west. And if we assume our diffusivities are constant and our spacing's constant, this just becomes 2K per delta X. Now, in this situation, the only thing we can control is delta T. Delta T is a time step that we're able to impose on our system because we've already picked our delta X. So if we solve for delta T, kick this over, drop that down, our delta T has to be greater than rho C delta X squared per 2. This has to be upheld. If you do not, horrible things are going to happen. And I think I have some videos. Oh yeah, I'll upload those videos towards the end. Actually, I got a really good one, and I got some bad ones. I got a good video, and then I got a bad picture. We'll share. Now, this has to be upheld for stability. And what we notice are a few things. Rho C per kappa, right? This is just alpha, your thermal diffusivity. And let me just check on Google before I say that. Thermal diffusivity is indeed, it's 1 per alpha. Yep, that makes sense. That goes back to differential equations. Sorry, Professor Goldie, I let you down. That's 1 per alpha. So really you have delta X squared per 2 alpha. Now your delta T is dependent upon delta X squared. And this is where the explicit scheme really becomes lackluster. Because if you want a relatively fine mesh to capture some resolution, because we're first order accurate right now, you need a really small delta X. Well, a really small delta X squared is a really small delta X, which means you need a really small time step for us to have stability. Oh no, that's bad. It's also then divided by 2. So this isn't good, right? Look at this guy. Just keep this in the back of your mind. That's ugly. Okay, so now what's really fun is Fluent. It's a semi-implicit solver. And here is a really basic video of an explicit scheme. I set this to fully explicit to match in-house numeric code. Like how Windows asks that if it's you after you already logged into your own computer. But the red region is indicating water. The blue region is indicating ice. The rainbow region is indicating a mushy zone that tells us that we are part liquid, part ice. And as we're applying heat to the left-hand side, we're seeing our water region is beginning to grow outward and propagate. And it almost looks like a caterpillar moving along. So this is a fully explicit scheme. The time step was on the order of about a microsecond. And this was a simple 1D domain with like 10,000 cells. And we're talking about a couple days worth of sim time to move. And if we look at the scale bar, 0.0005 meters, so half a millimeter. We moved about 1.5 millimeters after, a couple days. So that is an explicit scheme with an incredibly small time step, which is good. Now, what happens is if you pick too large of a time step, and I know this is incredibly hard to see, but I had to zoom out. Here's a red region, which is representing water. So if we're applying heat to the left-hand side and we have a huge domain of ice, we'd expect the water to form here on the left-hand side, right here, and this to be ice. And you go, okay, that looks kind of cool. We have water and then we have ice based upon our mass fraction. But if you look in the domain, you see, wait, I have some water existing. This should be ice. Well, the delta T was too large. And the information from the left-hand side got passed too quickly through our domain. And we go, oh man, that time step is too big. It doesn't work. And a really easy way to think about this is you want your delta T to be small enough. If we are trying to, let me draw this out. If we're trying to pass information here, J, about a flux, we want J to go from here and at most to our next interface, such that we can determine what's happening in our cell center. Now, if we send J through in our next time step, it has already moved down here. We've lost information about the interior of our cells. That is, you're passing the information too quickly through your domain. And that's why the explicit scheme for stability needs incredibly small time step, or we're going to begin to generate physically unrealistic results. So you go, okay, well, the explicit seemed really cool. It's going to be really easy to code, but man, this delta T is going to kill us. Yep, that's what it does. Now, let's move up. Let's say, all right, what happens if we mix our explicit scheme or implicit scheme? I.e., we set our weight factor to 0.5 and we construct the Crank-Nicholson scheme. We have something that is called unconditionally stable. Its stability is not conditional upon the selection of delta T. However, although it is unconditionally stable, our results might be garbage. What it means is, yeah, it'll run. We will get a solution. We shouldn't have too many issues with convergence. So the math is going to work out. Mathematically, we can actually obtain a solution to our system of equations, but does it mean anything? Probably not. We had a really amazing undergraduate student who's now at the University of Michigan. He was working with a PhD student on just doing some of that melt modeling. And let me show you guys a cool video. I like videos. So in their year of working on building a moving mesh model and the like, they created a wall of colorful pictures of things that never worked. And what's amazing about just anything computation is like when you run CFX and in 10 iterations, you hit the Planck temperature, you know you messed up good. And it's just fun to figure out why. But here's some of the work they did. This region right here is indicating where a cylindrical probe, just a cylinder, would be melting its way through an ice field. So this blue region is ice. The red region is water. The rainbowed region is ice-water interface. This probe's heated at the bottom in the sidewall. And actually what's happening here is you might be able to see it. All these little hash marks are the mesh, and this is an iterative remesh algorithm. So the probe would apply heat until enough of a unit cell layer was able to be melted, take monitor points, remesh the domain, move the probe down, and repeat the process. In doing this, though, they had some of the most amazing colorful pictures of where the temperatures were above the Planck temperature. Things were going crazy. And that was really related to the time step. They said, okay, well, we have, an implicit solver. Let's crank up the CFL. Yeah, just because it's solving doesn't mean you're going to get realistic results. So when we look at the Crank-Nicholson, we have to keep this in the back of our minds. When we look at our coefficient, and we set f is equal to a half, we're going to have AP naught minus A east plus A west divided by 2. And we can see this hanging out here. That if we put this as a half and a half, right, we're looking at the situation where we have AP naught minus A east plus A west per 2. That is the quantity that's leading TP naught. And we want this to be greater than 0. So we want this guy greater than 0 in this situation. Now, all we can say is AP naught is equal to rho C delta X per delta T. And we want this to be greater than kappa per delta X. Notice how we had this 2 down here. It cancels out the 2 that we previously had within our numerator. So when we solve for delta T, our time step, we're left with rho C per K. So you'd have delta X squared per alpha. Now, let's compare this. For our explicit scheme, we wanted delta X squared per 2 alpha. So right now, using the Crank-Nicholson, we can conceivably have a delta T that is twice as large of that of using our explicit scheme. And it's unconditionally stable. Yeah, it's going to run. Are results meaningful? Who knows? Now, this leads us to our implicit scheme. Now, the implicit scheme is really, really beautiful, but we have to be careful. Now, in our implicit scheme, we set f is equal to unity. So everything from our previous time step drops out. And we're left with AP TP is equal to A east T east plus A west T west plus AP naught TP naught. Hey, look. We don't have any more AP naught minus A east minus A west hanging out. So AP naught will always be positive, which means, hey, this is probably the best scheme, right? There is no delta T limitation. And right now, you might be popping open some champagne, celebrating, saying, hey, we have a scheme where I don't care about my time step. That's not true. Because if we once again pass the information too quickly through our system, we're going to lose that information in our cells. The solution is going to get smeared. And a really easy way to think about this, let's see, we can do carbon vortex shedding, right? And I'm sure there's dozens of people out there who might have done this and looked at the effect of the CFL number. Now, carbon vortex shedding is a really fun, simple problem to do. And what's beautiful is, say, using CFX, setting a low CFL number, and just using a really, really nice mesh with a low Reynolds number, even of 50, we can get vortex shedding phenomena. Now, this is completely CFL number dependent. And here I was just really hoping that someone did a study of a CFL number. Now let's take a quick look. And I might be able to tell you what's going on just based upon their simulation. Now it's a tutorial. Here are their results. So here's the evolution of the vortices existing behind their cylinder. And notice the symmetry right here of their midplane, right? Now you're beginning to get a little wiggle once the fluid domain passed over. Now, the ability to capture the wiggle here is completely dependent, number one, on the mesh, but also the CFL number. Now, you don't see any vortices breaking off and shedding. Not the best simulation. Now, let's look at this guy. I think this guy did a little better. Oh, pair review. How much I hate pair review. But anyways, what we see is, I'm just going to move along in their sim a little. Now, they didn't have that really strict symmetry we were seeing in that previous video. And you see asymmetry, and you're actually capturing these vortices, these eddies, detaching and moving downstream. And I'll put $20 on this. It's their solutions are probably heavily dependent upon the CFL number they specified, i.e. the delta T they picked. And I'm guessing, well, the first one was Fluent, which is a semi-implicit method. I don't know what SimFlow is. But even if you did this in CFX, if you set your CFL number too high, we would have got the same solution you're seeing from that Fluent model. And then if you began to decrease your CFL number, i.e. decreased your time step, you begin to pick up more of what's physically happening. So, long story short, you might go, oh, wow, the implicit scheme is the best. There is no delta T limitation for us to have a stable solution for my solver to converge. Yeah, but if your delta T is too large, you're going to be missing some of the stuff happening in that time period. If you're trying to capture vortices that are being shed at a frequency of 120 hertz, that means your time step should be less than 1/120th of a second. Probably a lot less to capture the evolution of it as well. Now, you might go, okay, so you can't get something from nothing. That's fair. But it all depends upon the problem you're modeling and what you're doing. And sometimes you just have to figure this out on your own, or spend some time on the forum seeing, what's a great delta T, what's a reasonable delta T to start the problem. Here's how I have everything set up. It is noted, though, that if you do have incredibly small time steps, the Crank-Nicholson scheme actually does have higher accuracy than your implicit, because you're now essentially pulling more information from more neighboring cells, both spatially and temporally. So Crank-Nicholson is sometimes pretty good, or depending upon the problem at hand, you could do a study. Vary your weighting factor from 0 to unity in increments of, say, 0.1, and compare your solutions. So for a type of problem, you might actually find a weighting factor of 0.7 is the best that you're working with based upon the physics you're modeling, and you can run that throughout the remainder. Now, these schemes, you're going to be using each of them in homework number 2 when we talk about a transient problem. And you're going to begin to see which ones are really good, which ones are okay. and they're fun. Now, additionally, something you also have to consider are source terms, because we didn't talk about those quite yet in the fullest capacity. And source terms are super, super useful. Now, what we're going to do is we're going to take our 1D diffusion equation and our transient equation, um, and we're going to go back to our original form when we just did, 1D diffusion. But here we're going to tack on a coefficient b. Now we're going to define a east, a west, AP naught, and AP just as we done before. But what we're going to do is when we define AP, we're going to have a west, a east, AP naught, and then we're going to introduce two components of our source term. SC, which is a constant source, and SP, which is the non-constant contribution within our system. And this gets baked into our new coefficient B. B has our constant source term, this is multiplied by delta x, because the source term is typically on a volumetric basis, but recall we were integrating over area. And then we're going to have AP naught, TP naught associated with B. Now, this is really useful because source terms appear in many ways, shapes, and forms. So we're going to be referring to, this set of equations because we have two examples associated with this. Now, what we're going to do is look at our 1D system where we express our diffusion equation as AP phi p. Now we're just going to jump back to phi for a conserved quantity is equal to A east phi east plus A west phi west. This is going to be our homogeneous equation. And we can apply our Dirichlet and Neumann boundary conditions as we had previously defined. Once again, A east, A west are defined as our area times our diffusivity per our spacing between our cell centers. Our AB, which is our coefficient for our cells, or really for our boundaries or interfaces existing in our boundary, is going to be 2 per delta x times our boundary diffusivity. AP would just be equal to A west plus A east plus AB, as we have defined here. You can easily tack on AP naught, TP naught. Now, what we're going to do is drop, really, the transient terms. They're, for the sake of showing source terms, they're really, really easy to tack on. As you see, the equations we kind of cast, these coefficients are easily just modified. Hey, if we want transient, throw this onto the coefficient. If we don't want transient, ignore it from our coefficient. So just for the sake of really focusing on the source term, we're going to drop the transient portion of it. So we're going to go back to our one-dimensional diffusion equations that are listed as follows. Now, we want to talk about source terms and how we have to consider it. Now, a source term can come in many ways, shapes, or forms. If we're talking about energy, our source term can be equal to Q triple prime, which reflects the volumetric heat generation rate. If we're talking about species or concentrations, we can define it as R, our volumetric reaction rate. Or if we're talking about any turbulent flow, we could talk about the production or dissipation of turbulent energy, turbulent kinetic energy, or viscous dissipation. So for our one-dimensional steady state diffusion equation, we'd have del by del x of gamma A del phi del x plus our source term dotted with our area. Our area is delta x delta z. Now, when we go through the integration process, just as we've done before, what we see is our integrated source term is multiplied through by the volume that our cell exists. So you can think about this. Oops, there's a y in there. Delta x, delta y, delta z. You can think about this as the differential volume our cell is occupying. Now, when we say S bar, this is more or less an average volumetric source term. Because within our little differential volume, we would have a source term, but it's going to be averaged over our domain. So really, we've just, if I go all the way back to the beginning, we've looked at this guy and just tacked on our generation. And we can easily tack on the transient contribution as well. Now, we have to discuss a little bit about this volumetric generation. And the best way to do this is an example. This is simply, ever so simply, incredibly simply, basically a constant value we're going to tack onto each equation. So sources, although they appear cumbersome, and we have to take an average source term acting in our differential volume, if we go up here, it's just going to tack on as a little constant value. So let's actually see how this works. Sources are going to be incredibly easy and something we can easily modify our transient solution to incorporate. Now, let's look at a really simple 7-node, 5-cell stencil, where we have a slab of material that has a length or thickness of 2 centimeters. So from end to end, this is 2 centimeters, or 0.02 meters. And we're going to assume a thermal conductivity of 0.5 watt per meter K, relatively low thermal conductive material. Now, we have a uniform heat generation rate of 1,000 kilowatts per cubic meter. And the left-hand side is going to be held at 100 degrees centigrade. Our right-hand side is going to be held at 200 degrees centigrade. We want to determine the temperature profile within the slab. So realistically, you would expect, if there was no volumetric heat generation rate, a linear temperature profile. But depending upon the strength of this, we might have a nonlinear temperature profile. And it might be skewed since our right-hand side is held at 200 degrees centigrade and our left-hand side is held at 100 degrees centigrade. Now, yeah, we can solve this analytically. It's not too hard, but let's use our finite volume method, pardon me, to see how we'd handle this. Because if we did that, then we can include things such as a transient response, temperature-dependent thermal conductivity, temperature-dependent heat generation rates, all that fun stuff that we can't do very nicely analytically. So what we're going to do is set up a really simple 5-cell stencil where we have our nodes 0, 1, 2, 3, 4, 5, 6. We're going to assume our delta X is constant for each cell. And we're going to assume delta X is the spacing in between each cells. So let's jump into this. Now, with our 1D diffusion equation, we're going to have Dirichlet boundary conditions and a volumetric source term. So we can say AP phi P is equal to A West phi West plus A East phi East plus AB phi B. Recall this is only applied when we're at a boundary, plus our integrated source term times the volume of our cell. And what we're going to do is assume that our interfacial areas are all the same, and we're going to set those as unity. We're going to assume all the spacing in between our cell centers is the same. We'll call this delta X, and we're going to define all the diffusivities at our interfaces to be lambda. So in doing such, we can set our coefficients. My apologies for the yawning. A West is equal to A lambda per delta X. A East is equal to A lambda per delta X. And A at our boundary is equal to A times 2 lambda per delta X. Thus, we have the following equation for our leading coefficient AP. AP is equal to A West plus A East plus A boundary plus SA delta X. Awesome. Now, all we have to do is apply this a few times over. Let's start with our first control volume. Now, AP would be equal to A west, and we're going to set this guy equal to 0 because we're going to evaluate AB. This would be plus A east plus AB. A east is equal to A lambda per delta x, and then AB is A times 2 lambda per delta x. Now, in this particular situation, we set A equal to unity. Lambda was 0.5, and delta x would be 0.02 divided by 5, or 0.004. And then a boundary, we'd have 2 times lambda, or 2 times 0.5 per delta x, 0.004. So AP is equal to 375. Okay, that's good. AP is also not negative. We don't care about that because that's not a transient problem, but we want that positive. So what we're going to do is populate really the first row in our coefficient. Our coefficient matrix, as well as our right-hand side. Now here was our initial equation, where we have AP phi p minus A west phi west minus A east phi east. Now when we look at this guy, for our first control volume, our center cell P is at cell 1, our eastern cell is at 2. A west is non-existent because we don't have a cell out here, but we have AB. So what we're going to have is AP, there is no west, minus A east is equal to A at our boundary plus our source term. Now this is the only main difference to the inclusion of source terms within either a steady state or a transient diffusion problem. We just tack it on. It is literally a constant that we are adding to our B matrix every term within. It is incredibly simple. So if we look at this, we found AP to be 375, and this would be multiplied by T1. We have no T naught because A west was 0. Then we're going to have minus 125. Oops, that's a 2. My apologies. I'll try to remember to fix that in the actual slides. And minus 125 T2. And this was our A east, right? Right there. 0.5 divided by 0.004. And if I double check my math, that indeed is 125. This becomes a negative quantity because we moved it to that side of the equation. Now what we're going to do is add AB times our boundary temperature. Our boundary temperature on the left-hand side is 100 degrees centigrade, and AB would be twice that of A east. So we're going to have 250 times 100. This would give us 25,000. But we also need to consider a source term. Our source term is our rate, and we are generating 1,000 kilowatts per cubic meter. So that's 1,000 watts per cubic meter. Now, since this was integrated over area, we need to convert this volumetric heat generation rate to really a flux on a per unit area basis. And to do that, we're going to multiply it by delta x. So we're going to take 1 e to 6 times 0.004, and this is going to add 4,000 to our first term in the B matrix. And it is that incredibly simple. And we could even do this for a transient problem. That'd be really fun. Even if your source term was a function of time. Oh, just imagine all the fun we could have. Okay, now for second CV, third CV, and fourth CV, this is really easy. There is no boundary, i.e. no edge of our domain we have to worry about. So AP is equal to A west plus A east, or 0.5 divided by 0.004, or 125 plus 125. Cool, that's really easy. So AP gets populated as 250 for our second, third, and fourth control volumes. A east and A west are both minus 125. There is no AB, no boundary coefficient or temperature we have to consider. And once again, we just consider our source term, 4,000 on the interior. Now note how this previously differed from a non-source 1D diffusion equation. The second, third, and fourth entries of our B matrix were typically 0. Now we have a source. We just simply add the constant. This is, I'm sorry, this is really simple, right? CFD seems really, really hard. Numerics applied to any diffusion problem seems really, really hard. We're just adding a constant to this. And here people pay ANSYS $200,000 for a license to solve some heat diffusion problems. I don't get it. Okay, last but not least, when we move to our fifth CV, we have west, we have P, we don't have east. A east goes to 0, AB exists, AB was defined as 2 times really a standard A east or A west. So AP, once again, is 375. We see that. A west is minus 125. But now we have to consider our boundary. So A west was 0. Sorry, A east was 0. Now, at our boundary, we have a temperature of 200. And we also have a boundary coefficient AB of 250, twice that of A west. So what we'd have is 2 times 25 is 50, 0, 0, 0, 50,000 hanging out from our boundary term, and then another 4,000 hanging out from our source term. We are left with this system of equations. Now, the only difference is S was a constant just added to each term in our right-hand side matrix. That's it. Nothing more than that. So source terms are relatively easy to incorporate. And we can see if we had a transient problem, we just tack on the source term too. Hey, it's a constant, throw it on. So if we solve this, what we're actually going to see, and I will try and make a decent enough plot for this. 1, 2, 3. This is our temperature. Our left-hand side was held at 100. Our right-hand side was at 200. So our first cell entry is 150. Our second is 218. Our third is 254. We have 258. We have 230, and then we're coming back down to 200. So the temperature distribution within the system is definitely not linear, and we see it is slightly skewed, right? Our highest temperature that we have based upon where our nodes are at is 258 at node 4. Now 5 points, actually 7 points is good enough to get a curve fit. And we'd be able to capture that nonlinearity. So source terms are a super easy incorporation to this method. Now, once again, I've been running on for about 45 minutes. The question for you guys is all that we have left in this updated lecture is talking about our convective boundary conditions. Our convective boundary conditions, it's going to be a somewhat simple modification, just like a source term. So we could take a break and do that. We'd probably have 10 slides left, or we could just try and go through them right now if you want, since we're on the source term train of thought. So what do you guys want to do? Anyone have any input?
I'm okay with keep going. Keep on going.
Okay.
Oh, yeah.
All right, Ivan and Carlos, you say keep on going. Let's keep on going. Maybe we'll end a little bit sooner. Okay. Now, we looked at source terms with the Dirichlet boundary conditions. Now, what's cool is we can kind of use source terms to help with our Neumann boundary conditions. And this is pretty cool. So let us consider the following situation. Say we have a convective boundary condition on our system, and we talked about that previously. Yeah, we can specify a flux, right? So when we solve for AB phi, let me jump back here. So many equations, so many. Right, when we had AB phi, that's for Dirichlet. And then we can have our given flux, Q, at our boundary, times the area of our boundary to handle our Neumann or our convective boundary conditions. So we did that a little bit previously. Now there's another way to approach this problem. Now let's consider a situation where we basically have a material where we are conducting heat through it, and then this heat gets convected away. Now we have to have continuity of heat, right? So Newton's law of cooling for a 1D system states the heat that's being conducted through a system, d by dx lambda a dt dx, has to be equal to that that's being convected away, where h is equal to your convective heat transfer coefficient. AS is your surface area. T is your surface temperature. And T infinite is your free stream temperature. Now, what's really cool about this is we saw, like, we could apply a boundary condition. Q at our boundary times the area of our boundary. That works. Or since, this is removing heat from our system, or potentially we could have it applying heat to our system, we could model it as a sink or a source, respectively. In this particular situation, we're going to assume T infinite, our free stream temperature, is probably less than that of our system. So this cooling phenomena, this convective phenomena, we can model it as a sink. That is, we saw how on our previous examples where we had, that source term hanging out as a constant over here, right? We can model cooling as a sink. So we put it on the right-hand side as something that is removing heat from our system. Now, this is great if we are now trying to model more of a physical system where we don't just have cooling via convection on one boundary of our domain. Maybe it's happening universally across our domain. And now we just model as a sink, which becomes really, really easy. So what we're going to do is we're going to define the following. If we assume lambda and a are constants, right? We have lambda a d by dx of dt dx would be equal to HAS refresh the screen. Hey. We'll have lambda a, they're constants, they're going to come outside, or once you apply that product rule many times over, you realize they just hang on the outside. HAS t minus t infinite. So what we're going to do is take lambda a and nope, the pen has now ceased in its entirety. Ivan and Carlos, the universe is against us. It's like, hey, you guys could get out early.
Sorry, my bad.
No, we'll blame Andrew. Okay, so that's dead. That is dead. That is awesome. No, but I can still move zoom. I just can't move the screen. Why don't you just work with me? This is not a great advertisement for anything Microsoft related. There we go. So, wow. Okay, we lost all that. So we have HAS T minus T infinite. So we're going to take this lambda A, put it over here, and we can define this variable. Versteeg defines it as n squared. You could call it n, you could call it whatever variable you want. So what's going to happen in this situation is imagine we have this rod and we have cooling going down the entire length of it. So in this situation, as opposed to modeling just a Neumann boundary condition on the end, we can model a Neumann boundary condition over the length of our domain. And what's incredibly amazing about this is our sink can be dependent upon the temperature of our cells. So if this is really hot here, and we have a convective boundary down here, you're going to have a temperature distribution, and the strength for which heat is convecting off can be dependent upon the temperature of each of these cells in your free stream. But we won't get into that just yet, but that's kind of like a little trailer for how we can use this little method here. So once we define n squared as our convective heat transfer coefficient times our surface area per our thermal conductivity per our, well, times our cross-sectional area of the member, we're left with this equation. d by dx of dt dx minus n squared, the temperature of our cell minus our free stream temperature being equal to 0. Now, what we're going to do is just do our volumetric integral, since this is purely a spatial term. We're going to set our defined quantity phi as temperature. Lambda is equal to our diffusivity. And when we say we integrate over volume, we're actually integrating over area, because this is 1D. But what we're going to do is integrate our left-hand side, d by dx of dt dx with respect to volume. And this gives us our area, dt dx, evaluate our east face, minus area, dt dx, evaluate our west face. We've seen this before when we constructed our 1D diffusion equation. Now what's going to happen here is n squared t minus t infinity. That's all a constant. We're actually integrating with respect to area. So what we're going to have is n squared t p minus t infinite a partial x is equal to 0. Now, what we did before is we used a backward difference scheme. dt dx evaluated at the eastern interface is te minus tp per delta x. dt dx evaluated at the western interface is tp minus t west per delta x. And our area terms all drop out. So we're left with n squared tp minus t infinite delta x. Now let's just rearrange a few terms here, because we're interested in solving for tp. If we group our like terms, we'd have 1 per delta x plus 1 per delta x tp is equal to 1 per delta x t west plus 1 per delta x t east plus n squared delta x t infinite minus n squared delta x tp. Now, what we're going to do is rewrite it in our standard form. APTP is equal to A west T west plus A east T east plus A boundary T boundary plus our average or our integrated source term. Now, in this particular situation, what we did was really took our area dependence out. So A west, which we typically defined as area times our diffusivity, now just becomes 1 per delta x. A east, which was our area times our diffusivity per delta x, is just 1 per delta x. So that remains relatively unchanged. It's just we were able to cancel out our areas and our diffusivities. So our weighting coefficient here, AP, is equal to A west plus A east, which we have defined, and not much different from before, just for this problem, they reduce down, plus our boundary, plus, and here's the kicker, we have n squared delta x. So this coefficient is in part due to that convective boundary condition that's being applied uniformly along our domain. Additionally, our integrated source term has to pick up the remainder. S bar is equal to n squared delta x t infinite. So it's a slight modification to the setup of the equations we had, but nothing too radical. So let's see how we apply this. And these equations are going to make a reappearance. Let's consider we have a fin. It's 1 meter long, so pretty substantial length. That we have a constant cross-sectional area. If the base of our fin is 100 degrees centigrade, the end of it is insulated, whereas the really exterior, the perimeter of this, is exposed to a free stream temperature of 20 degrees centigrade, and we're given n squared is equal to 25, we want to determine the temperature distribution within. And this isn't hard. What we're going to do is do what we always do. Take our governing equation, which was this guy right here, and go through, solve AP based upon A west, A east, see if we have any boundaries, calculate our source. Now our source in this situation was this one term hanging out right here, our n squared delta x t infinite. And this is really acting as a sink because it's pulling heat away from our domain. So for our first control volume, we have 100 degrees centigrade Dirichlet boundary condition. We don't have a western cell, that's 0. So we have A east plus A boundary plus n squared delta x. So A east was 1 per delta x. Since this was a meter long domain, we have 5 control volumes, that's a 0.2. A boundary is just 2 times A east, so you'd have 2 per 0.2. And our n squared delta x becomes 25 times 0.2. And recall, this guy was due to the fact that we had the n squared delta x TP hanging out. So AP is equal to 20 in this situation. So we're going to populate 20, and A east is -5. Now the left-hand side, we had no A west to that, so that drops out. Now for our right-hand side matrix, we have A at our boundary times our boundary temperature. Our boundary temperature was 100 degrees centigrade, and AB would be 2 of A east, so that's 10. And then what we have here is S bar, our integrated source term. Now recall S bar is equal to n squared delta x t infinite. So we have n squared, which is 25, delta x is 0.2, and our free stream temperature was 20. So this is going to populate these two combined. A nice set of terms. Our first entry in the right-hand side matrix. And I'm just double checking my mental math. That's 1,000. Yep, that is definitely 1,100. Cool. So really, our convective condition is modeled as a source. It's going to populate our right-hand side matrix, which is awesome. Now, our second control volume, we have nothing in the boundary, So AP is equal to A west plus A east, or 1 divided by 0.2, which is 5, plus 1 divided by 0.2, which is 5, or 25 times 0.2. I'm just going to multiply 25 times 1 divided by 5, which is plus 5, is 15. So our next three diagonal entries are 15. A west and A east are both minus 5. And we had that fantastic S bar hanging out. Our source term, once again, from our convective boundary condition. Nice. Tack on 100. Our fifth control volume, we have nothing in terms of an eastern cell, because that's the end of our domain. And we have nothing, so AB phi is 0 because it was insulated, because we'd have QB times AB, and QB is 0 flux. We said it was perfectly insulated, so that's 0. And then we just have n squared delta x. So AP in this situation boils down to 10. We'd have 5 plus 5. 10 here, minus 5 stays. And then for our governing equation, AB phi b was 0. Our volumetric heat generation term was once again 100. So S bar gets added. So we can think of, convection as we could apply as a source through our system. Now, let's just do one thing. We're assuming that this unit cell is representing the entirety of the rod. Now, if you're actually modeling a rod, what you might do is have more mesh divisions on the inside, where you have lots of mesh. And then this method is ever so slightly different, because you actually have to apply those boundary conditions to the exterior of the cells, and the interior of your cells are conduction only. But for a problem as simple as this, it works out well. Now, when we do this, we're going to have a pretty unique temperature profile. If we looked at our system, this is X. You have our first node, second node, third node, fourth node, 1, 2, 3, 4, 5. Here's our boundary. Here's our temperature. So you're going to start at 100. We're going to drop down to, that's about half, 64. And 36 is about a third. 26 right there. And we kind of have this exponential decay going on with our temperature profile. And you can compare that to the analytic solution, where you could solve for T. And this requires the use of the hyperbolic cosine, which is common in heat transfer. But that's neither here nor there. What's really cool is our source terms, if we jump back, can act as a universal boundary condition to that cell. So source terms are super, super powerful, and they're so easy to incorporate within the finite volume method. We just tack on a constant value. This, of course, isn't talking about nonlinear source terms, which we'd have to spend a little time later on with. But as it stands, like, we could even tack on this source term formulation to our transient problem. Super easy. Just add S onto the end, and we're done. So that concludes, I think, almost everything we need to cover for one-dimensional diffusion. We've covered non-uniform grids, we covered source terms, we covered transient analyses. The only thing we'd have to do is covering, temperature-dependent material properties, and a little bit of multiphysics. But multiphysics in of itself is just a source term. So we will kind of look at how that's done. I think what's going to be really fun is we'll try and do an example of a conductor that has temperature-dependent diffusivity, temperature-dependent electrical resistivity, and is carrying a current, and looking at how those temperatures evolve and all that fun stuff, assuming a uniform current density is flowing through it. And just how we set up a iterative algorithm to handle temperature dependence. But besides that, I think we've really covered any and everything we can diffusion related. So next class, what we're going to do is get into 2 and 3D diffusion. Talk about how easy this method is to extend in different dimensions. So we'll combine both of those, and we'll talk about the tridiagonal matrix algorithm, the pentadiagonal matrix algorithm that's used to solve those coefficient matrices quicker and faster than just brute force inversion. And that will hopefully get us into a really good position to start learning some of the numeric tools to handle these types of problems, generate the meshes, run the models, post-process the results compared to our codes. And that would really set us up to move into flow. So with that, I know it's a bit quick. I'd suggest now that you guys have the MATLAB scripts so far to take them and either write your own or update them to go through these examples again. See if you're getting the same temperature outputs. And what we'll do next time is I'll be providing the analytic validation portion of your next homework assignment, where we basically do 2D transient evolution of temperatures and start talking a little bit more about those types of problems. But with that, we're done for the night. I'll see you all next week. If you have any questions, stick around. I'll be happy to try and answer them.